Today I want to talk a little bit about Hardy-Weinberg, and in particular where the allele frequencies are coming from when we're doing a Hardy-Weinberg. So when we're talking about a Hardy-Weinberg population, we're talking about a population that's in equilibrium where the allele frequencies are not changing. So there's going to be no change in our allele frequencies. So what we can do with Hardy-Weinberg is for one of these kinds of populations, we can actually predict what the genotype frequencies will be in the next generation because there are no allele frequency changes. So let's start out just thinking about a population that has two alleles. We're going to just call these for now big A and little a. Your book calls them A1 and A2. That's fine too. So the frequency of big A, meaning the number of big A alleles over the total number of alleles in the population, we're going to just call this number P. And this is a number that's going to be between 0 and 1. If the number was 1, then the big A allele would be 100% in the population. If it's 0, that means that there are 0 big A alleles in the population. The frequency of little a, we're going to set this to Q. And again, this can be 0 to 1. If we only have 2 alleles in the population, then the total frequency of big A plus the total frequency of little a is going to have to equal to 1. This is our first thing that we figure out when we're doing one of these. This is going to be true whether or not we're in Hardy-Weinberg. As long as we have a 2 allele system, this is what we're going to see. So what is going to happen when these guys start mating? What kind of genotype frequencies are we going to expect to see in this population? So we're going to be thinking about the gametes in the population. And so we're going to have eggs and sperm. And the eggs and the sperm can be 2 different types. An egg can either carry a big A allele or a little a allele, and a sperm can either carry a big A allele or a little a allele. Now keep in mind this is just one genetic locus. We're only looking at one genetic locus in Hardy-Weinberg. We're not looking at all of them. So to figure out the genotypes, we can just make a little Punnett square. Along one axis, we're going to put all of the possible sperm, and on the other axis, we're going to put all of the possible eggs. So here we're going to have our egg axis here, and here we're going to have our sperm axis going down. So our sperm can be big A or little a, and our eggs can also be big A or little a. So when we have a big A sperm meet a big A egg, that's the only way, or a big A egg meet a big A sperm, that's the only way we're going to get a big A, right? So the frequency of finding this big A is just going to be the proportion of big A eggs times the proportion of big A sperm. Right? So that's going to equal the frequency of the big A sperm compared to all the sperm, so that'll be P, times the frequency of all of the big A eggs, which will also be P. So this is going to equal to P squared. So the P squared is the frequency of the big A genotype. Our next genotype is going to be big A little a, and the frequency that we find this genotype is going to be the frequency of getting one of these big A eggs and one of these little a sperm. So that's going to be P for the big A egg times Q for the little a sperm. Our next genotype that we have on here is going to be another big A little a, but this time we're getting the big A from the sperm and the little a from the egg. And this is also going to have the same frequency as this one here. We're going to have a big A frequency of P times the little a frequency of Q. Now here our last square is going to be reserved for the little a egg plus the little a sperm, or the little a sperm plus the little a egg. And so the frequency of this is going to be the frequency of the little a eggs, which is Q, times the frequency of the little a sperm, which is also Q, and so this is going to give us Q squared. So now remember, when we're talking about statistics, when we say that 2 things have to happen at the same time in order to get a result, that's an AND statement. To get a big A genotype, we need a big A sperm and a big A egg. And in that case, we multiply the 2 terms together. If we have an OR statement, meaning that to get a big A little a phenotype, we can have a big A egg and a little a sperm, or a big A sperm and a little a egg, we add if we have OR. There are 2 possibilities here. So because of that, our genotype frequencies, AA, so the frequency of AA the frequency of big A little a, and the frequency of little a, these are going to be p squared. There's only one possibility, no or statement. This one is going to be 2pq, pq plus pq, so 2 times pq, and this one is going to be q squared. Since these are all of the genotypes in our population, if we add them all together, they have to equal to 1, okay? Because these are the only genotypes we have, so the frequencies of all of these genotypes must equal to 1.